All right, chapter 2, image weighting and contrast. Usually like to do this one in person so I can do a little dance in front of y'all and keep your attention span. But since I can't do that today, hopefully you can force yourself to pay attention and to understand this, because this is a very important part of MRI in general. Very important to understand as a technologist, and definitely important to understand going forward so that we can continue to have the discussion of MRI physics. So please do what you can to pay attention, whatever that needs to be. Also, make sure you're asking questions as we move along. Weighting and contrast. Weighting is a weird word for this, but we'll find out why. Okay, find a button here to move this along. Not working. There we go. All right, contrast. Contrast, what does that word mean? This is the definition of contrast. The state of being strikingly different from something else in juxtaposition or close association. Being able to see the difference between objects is important in MRI, right? So if you can see here, if you look at these, if you imagine that there's not like an outside border here, there's not very much of a difference. There is actually, there's a slight difference between this inside and this outside here, but if you were to ignore this border, it'd be very hard to see, right? They're basically the same. There's not a lot of difference here. Medium contrast, there is a slight difference. It's not a lot, but it's definitely more than this, right? So we can definitely see that there's a circle within this other purple square right here. And then here, high contrast. There's a vast difference in colors between these two different objects, right? Like I was saying, I think I made the analogy the last class we were in. If I were to paint or write something up here in white, you would have a hard time seeing it, right? It would be the most beautiful thing in the world, but you wouldn't be able to see it unless I had contrast, unless I had something that looked different from what the background is. So in MRI, that's important so that we can see the differences between different anatomy, different differences between anatomy and pathology, so that we can find out what's going on there and we can diagnose. Right. All right, image weighting. Contrast in MRI is achieved by taking advantage of the differences of T1 and T2 times and proton density of tissues. Remember, we've talked about what the T1 and T2 times are. We'll talk more about what proton density is. But we're basically exploiting the differences of the time it takes for different tissues to recover longitudinally and for the time it takes for different tissues to decay transversely. Also, how many protons are there to begin with is going to determine how much overall signal we could start off with. The reason we call it weighting, though, is because T1, T2, and proton density properties exist in every image. We can't get rid of them all. We can get rid of T1 weighting if we wait long enough. But typically, these properties are going to exist in every image contrast. But what we do is we take the steps to weight the image towards a contrast that is defined more by T1, T2, or proton density, if that makes sense. So we're always going to, every tissue has a T1 and T2 time, right? It has a certain amount of proton density as well. So that property is going to show up somehow in our image, but we are going to manipulate the parameters so that the contrast is weighted more towards either T1 recovery, either more towards T2 decay, or more towards the amount of protons exist within that tissue. That's why we call it weighting. When people first hear that word weighted, what does that mean? That doesn't make any sense. It's because we're pushing the contrast to be more affected by T1, T2, or proton density. Here are our classic weightings. There's a lot of different subtleties of this and different ways that we can change our contrast, but these are the three basic ones that we'll talk about today. T1, what do we notice?
Water is dark, or the CSF.
Yep, CSF is definitely dark. And see, there is white and gray matter contrast in there though too, right? We can see white and gray matter have different signal intensities, so we do get that contrast in there. Then you get T2. T2 is like almost the opposite. We have bright fluid now, right? We always say in T1, we like to say that fat is bright and fluid is dark. On T2, we say the opposite. Fat is dark and water is bright. And these are just generalizations. As we start to progress in this conversation later, we'll talk about more of the subtleties behind that. But it's a useful tool to talk about T1 contrast having dark fluid and bright fat, and to talk about T2 contrast as having bright fluid and dark fat. And then proton density. What do you notice about this one?
Not a whole lot of contrast.
Yeah, that's great observation. There's not a lot of contrast. It's definitely we can see the differences, right? But it's not as vast. There's not as great of contrast as there is in T1 and T2. There's places PD we use it a lot, and we're doing other things to get contrast because there's a lot of signal. There's a lot of SNR in proton density, so we can exploit that and then utilize things like fat suppression to help us to get contrast as well. So PD is not typically used in the brain too often. So when we talk about contrast parameters, we have intrinsic and extrinsic contrast parameters. Intrinsic contrast parameters are parameters that are inherent to the tissue. They're part of the molecular properties of the tissue, and they cannot be changed by us. We cannot go and change the T1 or T2 time of a certain tissue, right? We can't change its proton density, and then flow. Obviously, we can't change the flow of. Oops, this mouse is not doing too well. I apologize. We can't change the speed of flow. We can't change something called apparent diffusion coefficient or ADC. We're not going to talk about those today. We're just going to talk about the top three. So don't worry about flow and ADC. We'll talk more about those in physics too and how they affect our contrast. But obviously, we can't change the T1 recovery time of fat. Right? That's not something that I can go in and change. So it's intrinsic or inherent to the tissue. So a couple things that affect intrinsic contrast is the molecular tumbling rate matching the Larimar frequency of hydrogen. Think about the molecular tumbling rate as kind of like the vibrational rate of a molecule. It's a little bit more complex than that, but you can kind of think about it like that. Like everything's kind of moving around at a particular rate. There's vibrational frequencies with all different types of molecules and atoms. So molecular tumbling rate is like sort of like a frequency that exists within certain molecules. And if that is close to the Larimar frequency, there's a good match there, which allows for an efficient transfer of energy. Right? Remember, think about it kind of like resonance on a different level, right? Remember, resonance is energy transfer between two similar oscillating systems, right? If they have the same frequency, we can efficiently transfer energy between them. So there's a good match between the molecular tumbling rate, which you can think about as just the vibration of the entire molecule itself, and the Larimar frequency. Then there's efficient transfer of energy between hydrogen nuclei and the molecular lattice. When there's a bad match, the energy exchange is not as efficient, right? We can think about that. We can't add energy to something if we have it at a different frequency than the natural frequency of the system. So this is important for both T1 recovery and T2 decay, right? If something has a molecular tumbling rate that matches the Larimar frequency, then T1 recovery is going to happen quicker because we're going to be able to transfer that energy back to the molecular lattice quicker and allow for recovery. Oops. Oh man, I have to figure this out, sorry. might have to stop this share. I'm just gonna have to do it like this. All right. Also, something that's an an intrinsic contrast parameter is the how closely the molecules are packed together. So different molecules are gonna be more dense, right? They're gonna be closer packed together. In tissues like that, where the molecules are closely packed together, there's going to be a more efficient interaction between magnetic moments. Remember, we called T2 decay spin-spin interactions, right? So it was like spins affecting other spins. So the closer the spins are together, the more likely they're going to affect each other, right? Does this make sense? So the closer the molecules are packed together, the closer the hydrogen is together, the closer the spins are together, the more efficient or the more often T2 spin-spin interactions are going to happen. So this definitely affects the T2 decay process. Tissues that have closer packed molecules are going to have quicker T2 decay than tissues that have further away, or the molecules that are free flowing and further away from each other. Fat has molecules closer packed together, the hydrogen's closer together, therefore fat is going to have a quicker T2 time than water. Does that make sense? And then the proton density. Fat has the highest proton density of all tissues in the body. This means that there are more protons per given volume of tissue than in any other. So think about it, if I fill a box with fat, and then I fill the same size box with water, there's going to be a lot more protons in that box of fat. If there's more protons, what else increases? What do the protons all add up to be?
NMV.
Yep, exactly. So fat per given volume is going to have a larger NMV than water in that same volume. That makes sense? So if I have 1 cup of fat and 1 cup of water and I put them in the main magnetic field, that might be the water's NMV. And that might be the fat's NMV, right? And then this determines how much magnetization we can put into the transverse plane, right? So those are all the intrinsic contrast parameters that we'll talk about. Extrinsic contrast parameters, these are parameters that you change as the MRI technologist. In fact, you will change them quite a bit, depending on what you're trying to do. Parameters that can be changed are under our control. They are TR, TE, flip angle, TI, turbo factor, echo train length, and B value. We will not talk about the last 3. Today, we're going to focus purely on TR, TE, and flip angle. Those other ones we'll talk more about in physics too. So breaking it down, making it a little bit easier so that we don't over jam-pack our brains with all of this information, okay? What's the difference between extrinsic and intrinsic contrast parameters?
The extrinsic ones you can change, the intrinsic you can't.
Exactly. What's an example of an intrinsic contrast parameter?
T1 recovery.
There you go. T2 decay, proton density, and then just kind of understand what can potentially affect T1 and T2 relaxation. Now it's going to get weird for a minute. This always gets everybody, but it's okay. We're going to talk about the spin echo pulse sequence. The reason I like to do this right now is because generating contrast between spin echo and gradient echo is a little bit different. It is based on the same thing. It's just you have to understand the mechanisms of the pulse sequence to really understand why we're doing it this way. So um, notice here we have our RFT. Does anyone know what that stands for? Obviously, radio frequency energy. That's one of our
Transmitter?
yields. Yeah, it's our transmit, and you're exactly right. This is our RF into the patient. This is the RF back from the patient. RF receive, RF transmit, RF receive. Notice we have a 90 degree followed by a 180 followed by the signal. In the past, I've told you that we just excite and then we listen back, right? Excitation creates transverse magnetization, and at some point we listen back, we collect the data back. We actually don't really do that. We have to do something else first. And there's a couple reasons for this. One of the main reasons is that K-space, where the data is stored, so write this down, all the raw data, which is these echoes that we collect, all the signal that we collect from the patient has to be stored in a place called K-space. K-space is a mathematical location that takes essentially digitized waveforms and turns it into an image. And in K-space, we have to have symmetry.
Brian, can you repeat that? It detects digitized what?
K-space is a mathematical place where we take digitized waveforms and turn them into an image. So it's basically just a place where we put all the raw data, right? We have to turn on the coil to get the signal back from the patient. That signal is measured and put into K-space. Just a mathematical plot, essentially. It doesn't look like anything to us, but it's essential in the image creation process. And K-space has to be symmetrical. There's got to be some symmetry involved in it.
Question, are you saying K-space?
K with a K. Kick.
Oh.
Yeah. So, what I've said in the past, or what we've already learned, is that we excite, we have transverse magnetization, and it decays away, right? If I were to turn on my coil after excitation, we're going to measure the signal decaying, right? We have a lot of signal, and then that transverse magnetization goes away. It decays down to nothing. Is that symmetrical on this axis? It is not. That is more symmetrical. So K-space needs to see the signal grow and then go away. That's one of the things that needs to happen. So if I were to take this and put it in K-space, I would have symmetry. This does not have symmetry. Following me? If you go back to the PowerPoint, notice this pretty little echo right here. If you draw a line down the center, it's a mirror image of itself, right? There is symmetry there. Another reason we do this is that decay, transverse decay, not only happens from, well, hold on, let me ask you this. Why does this happen? Why does transverse decay happen? What have we talked about so far?
Because the protons are going.
Spin.
There we go, I heard it. Protons affecting each other, right? There's spin-spin interactions, pushing on their little magnets pushing on each other, causing dephasing, right? We also call that T2 decay, right? That is not the only reason this happens. There is another reason that we have dephasing.
T2 star.
T2 star, there it is. So let me go to this real quick. In previous weeks, you learned that transverse decay, also known as dephasing, is due to T2 spin-spin interactions, but that is not the whole story. The protons lose phase coherence due to magnetic field inhomogeneities and susceptibilities. We learned about those two concepts last week, right? What is inhomogeneity?
Evenness?
Yeah, inhomogeneity is unevenness of the field, right? So the field strength being not the same, right? If the field strength is not the same, what happens to the Laramar frequency?
It changes depending on the tissue.
It changes depending upon the field strength, right? So if I have part of the magnet that's 3 Tesla and then I have another part that's 2.9 and then 3.1, am I going to have protons processing at the same frequency?
Absolutely not.
Not, right? How am I going to keep phase coherence if one is going faster than the other? We're not, right? So due to the inherent inhomogeneities of the magnet, we lose phase coherence very quickly. Therefore, we lose transverse magnetization very quickly. Spin-spin interactions are also happening, but in addition to that, there is inhomogeneities. Also, what was magnetic susceptibility? What did we define that as?
And an object is basically it's easier for an object to get influenced by a magnetic field.
Yep, it's matter's ability to influence a magnetic field, right? So there's different types of susceptibility. We have ferromagnetic, diamagnetic, superparamagnetic, and paramagnetic, right? So what that means is that when we put matter in the magnetic field, it's going to change the field strength, either weaken it or strengthen it to some degree, right? It's never going to stay exactly the same. That is essentially another inhomogeneity, right? Just by putting tissue in the magnet, it changes the field strength. And if we change the field strength,
So would you say like,
go ahead.
so we've said previously that these zeros homogeneous, but there could be areas where there's homogeneity, right?
Yeah, we're never going to get a perfectly homogeneous. Also, by putting tissue
So it's
into
not
the magnet,
like,
it's going to be inhomogeneous as well. It's going to create a susceptibility which makes it not even anymore, right? So, in theory, we would love to have a perfect 3 Tesla, 1.5 Tesla magnet, but we can't make that perfect. Also, just the fact that there's tissue in there, which we're imaging, creates a susceptibility, which causes even more of an inhomogeneity, right? That means that all the protons within that given imaging volume are experiencing slightly different field strengths, meaning they are going to process at slightly different frequencies, thus go out of phase very quickly, right? That type of dephasing is known as T2 star. We just call it that. There's dephasing due to spin-spin interactions. We call that T2 decay or dephasing. But then there's also a quicker dephasing due to inhomogeneities and susceptibilities and the fact that protons can't process at the same frequencies when we have susceptibilities and inhomogeneities.
Brian, correct me if I'm wrong, but so T2 star is pretty much something that we don't want to happen, but it's something we can't control.
We can think about it that way. And spin echo, yeah, we can think about it that way. We do utilize it sometimes, but we'll get there. So yes, if you want to think about it like that, that's perfectly fine for now. Because we have this quick dephasing due to susceptibilities and inhomogeneities, we can never truly measure T2 interactions unless we do something. That is why we use the 180-degree refocusing pulse. So essentially what happens is we excite, we have transverse magnetization, it decays away super fast, and then we transmit another pulse, which I'll show you some models of in just a second. That transverse magnetization then again grows and then decays again. And we measure that growth and decay, and that is called the echo. Let's take a look.
Okay, starts to decay away, so they're out of phase. So if we were measured at this time, we see the signal.
Whoops. So a couple things. Close that. Each of these like purple arrows is representing individual magnetic moments, right? Just the transverse component of each one of those individual magnetic moments, right? So we can see the transverse magnetization is decaying.
Diminishing. They get out of phase, it tends towards zero, and then we flip around the other way. In the rotating frame reference, those fast ones catch the slow ones, and there we go. A sort of bada bing, bada boom, they refocus, and we measure now, the signal comes back.
So the 180-degree refocusing pulse flips them 180 degrees through the transverse plane.
Brian. So pretty much focus pulse is just to like, to recycle the signal, right? As they flip it over.
It's to get the signal back, to eliminate dephasing effects due to inhomogeneities and susceptibilities. It's to get that signal back. Because the signal that comes back is actually a little bit less than it was at the beginning, because true T2 interactions are still happening. Because true spin-spin interactions, the interactions between spins, cannot be eliminated. We're eventually going to get full decay no matter when we transmit that 180 degree. If we transmit it way down the road, right? If we excite and then we wait and then we wait and then we wait and then we refocus with the 180, that signal is going to be pretty weak when it comes back in our echo, because true T2 interactions are still happening. We can eliminate the dephasing due to the inhomogeneities and susceptibilities, but not due to spin-spin interactions. Notice here, when it came back together, they're still not perfectly in phase. And that is due to true spin-spin interactions getting the protons to be slightly out of phase when we collect that echo. So let's go back to the 180. What's happening is that when we have differences in precessional frequency, some are going to be slower and some are going to be faster, right? So if I have a bunch of protons together processing, some of them are going to be processing a little faster and some of them are going to be processing a little bit slower, right? So they're going to fan out. Does that make sense?
Yeah.
Right? So let's say these are the faster ones, these are the slower ones, right? It fans out like this. 180-degree refocusing pulse flips it through the transverse plane. Now, the slow ones are in front of the fast ones, right? So what happens when the slow ones are in front of the fast ones? They eventually catch up. So there are some analogies for this, like a race. If people are running or racing around a track, right? Slowest person is going to be behind at some point. Fast person will be ahead. And then we tell them to go 180 degrees. They're going to flip around. And now the fast person will be behind, right? And eventually they will catch up again to each other. So let's watch that one more time.
And if we let it go further, the signal goes away again.
"90-degree excitation pulse."
Okay, starts to decay
phasing
away, so
immediately.
they're out of phase. So if we were measured at this time, we see the signal is diminishing. They get out of phase, it tends towards zero, and then we flip around the other way. In the rotating frame reference, those fast ones catch the slow ones, and there we go. A sort of bada bing, bada boom, they refocus, and we measure now, the signal comes back. And if we let it go further, the signal goes away again.
And it will continue to dephase like that because the inhomogeneities and susceptibilities still exist, right? We're just trying to get the protons to refocus to compensate for the fact that we have inhomogeneities and susceptibilities. So we start with a 90-degree excitation pulse, flip the longitudinal magnetization in the transverse plane. It decays very quickly in the transverse plane. Why? Why does it decay so quickly?
Because of the inhomogeneities and susceptibilities.
Yep, because inhomogeneities and susceptibilities cause the protons to process at a variety of different frequencies, causing faster ones to go ahead of the slower ones, right? So we get a rapid loss of signal. We call that rapid loss of signal the FID, free induction decay. We wait a certain amount of time. We transmit a 180-degree refocusing pulse. The 180-degree refocusing pulse takes the protons and flips them 180 degrees through the transverse plane so that now the slower ones are ahead of the faster ones. And then we wait longer, we wait enough time, they finally catch up with each other at exactly double the time between the 90 and the 180. We get the center of the echo, also known as the TE. Following me? All right. So I'm just going to read this one more time. T2 spin-spin interactions is not the only reason we have dephasing, loss of transverse magnetization. It's also due to magnetic field inhomogeneities and susceptibilities from tissue and air and everything else being inside that magnet. That type of quick dephasing is called T2 star. We can use a 180-degree refocusing pulse to eliminate the T2 star effect so that we can see dephasing due only to true T2 spin-spin interactions. So now the signal we measure over here, the amplitude or the amount of signal is going to be determined by the amount of T2 decay that happened, right? So T2 star, let's talk a little bit more about that. No magnetic field is completely homogeneous, and adding any matter to the magnetic field also causes the field strength to change locally because of magnetic susceptibilities. These mechanisms cause protons to dephase quickly. So we can see here a homogeneous field that doesn't really exist. We have cold spots and hot spots where it's a little bit weaker and a little bit stronger. That's going to cause the protons to process at different frequencies, causing the signal to decay very quickly. And we can see that decay is the T2 star curve, right? How fast does that decay happen? It's based on the T2 star. Here's another one. Right after the 90, if we were to measure the signal, it would be the most signal that we could possibly measure, right? If we turn on the coil, we would measure decaying signal. But right here, right after the 90, we would have the most transverse magnetization possible, right? And then it would decay quickly. Once again, why don't we put this in decay space? There's a couple reasons, but one of the reasons I just talked about. Why don't we record this? Why don't we just turn on the receiver coil right now?
It's not symmetrical.
Yeah, there's no symmetry. There's also no contrast, potentially, right? We just did it right away. But yes, that's what I wanted you to say, was there's no symmetry there. We wait a little bit. 180-degree refocusing pulse, right? That signal is going to grow again, and we're going to create an echo. Notice that the echo, the amplitude of the signal, is a lot less than it was at the beginning. And then if we waited even longer and then transmitted another 180-degree focusing pulse, we get another echo. What do you notice about echo 2 compared to echo 1?
Getting smaller.
Yeah, it's lower amplitude, right? Less signal. Why is it less signal?
Because the protons cannot absorb the energy as much. So they need another.
It's because we have true T2 spin-spin interactions that are happening, also known as T2 decay, that we can't negate, we can't minimize. It's always going to happen. Right? So we can put the protons back together, but they're never going to go 100% back together because true T2 interactions are always going to, they're non-reversible. What's reversible? T2 star decay is reversible. T2 star effects cause the free induction decay. This is known as the FID. That's what the reason the FID happens is because of T2 star effects. If we refocus the FID with successive 180-degree refocusing pulses, we will collect echoes with diminishing signal strength. The loss of signal between subsequent echoes is due to true T2 spin-spin interactions. Once again, the 180-degree refocusing pulse cannot eliminate true T2 interactions.
What did you mean by T2 stars reversible?
We can eliminate the dephasing, right? We can rephase the dephasing due to T2 star. That's what the 180-degree refocusing pulse is doing for us.
Is that what you mean by reversal, the refocus pulse?
Yes. Reversing T2 star effects are dephasing from inhomogeneities and susceptibilities, right? So reversing that would be to rephase them to eliminate dephasing due to T2 star effects. Try not to blank out. Try to figure out in your mind. I know this is difficult, but try to figure out the questions that you need to ask to understand what's going on here because this is important. Here's some videos that might help. That one up there, that's Grand Prix video. Let me see. I think you can actually grab these and I think I have them in Canvas. These videos have no sound, so you're not hearing anything that's how it's supposed to be. So here, I'll do this one first. So 3 different vehicles. They were all in phase at the beginning, right? Faster one, medium fast one, and the slow one, they're going to go out of phase quickly. Complete dephasing, no more transverse magnetization, thus no more signal being induced in the receiver coil. Flip them 180 degrees. The reason this model is a little bit funky and not perfect is because the protons aren't switching direction, right? They're continuing to process the same direction. They're just flipped so that the slower ones are behind. So they don't actually flip their direction. They go 180. They kind of think about it as like a flip, like a pancake. And then this one right here, they could show you see how this would be the receiver coil and see that no signal is being received and how it's going to start to be received again and grow as the protons come back together. This model is not perfect either because it shows them come back in phase completely, which they don't go back into phase completely. But you can find all of these in Canvas under videos in Module 4. How you feeling about this so far?
For the T2 star on the slide where it says T2 versus T2 star. So pretty much, I just want to go over the FID. So the FID once, because you said everything is uneven. So how do we
What do you mean by everything is uneven?
I mean the just like the echo 1, echo 2, and then the 90-degree pulse, everything is it's not what'd you say, symmetrical? So
There's symmetry here. There's symmetry here, right?
so just
No symmetry here.
okay. And um
So the FID, echo 1 and echo 2, they're decreasing in amplitude every time because of true T2 decay.
okay,
So let's say we were just scanning water right here.
okay,
This would show the T2 decay of water, right?
right.
But in reality, water's decaying, the signal's decaying much faster, right? Decays super quick because of T2 star effects.
Right.
We reverse those and have the signal come back and then dephase again. That is that's symmetry right there. That is an echo that we can collect and put into K-space.
Okay. And
Not
then
as high of amplitude as the original signal because we waited a certain amount of time to collect it. But that's
and
fine because now we have T2 information in there.
right. Thank you. T2 star is just the direct definition is just the occurrence of what happens during a T2 because of the susceptibilities and inhomogeneities, right? That's
T2 star is the dephasing of the protons due to magnetic susceptibilities and inhomogeneity. The
okay.
rapid dephasing of transverse magnetization.
Okay, cool. Thank you.
I got a question
Yeah.
on that same image. So we see the T2 decay line, and that limits the transverse magnitude of when we're offsetting T2 star decay recovery. If we set another 90-degree pulse, would the T2 the regular T2 recover back to the full transverse magnitude, or do you have to wait for the longitudinal recovery as well?
We're going to get pretty far ahead if we think about it. We are going to typically wait for most of the transverse magnetization to completely decay before we transmit again. We can have a side conversation about this, but essentially any pulse will create an echo, not just the 180. I like that you're thinking that way, but just try to think about it as if we did send in a 90, it would refocus some of the magnetization, but not all of it. So we would get an echo again, just not as much as we would with the 180. There's a lot of quantum physics aspects of this that are just that break down this model. But we typically would not send in another 90 again until transverse magnetization is completely gone and we have longitudinal recovery. Because the 90 is what it's going to take longitudinal magnetization and flip it into the transverse plane. So
That makes
that's
sense. Yeah.
why the models typically look more like this, like a spin echo model we're going to have. And then we're going to wait a long time. I don't have enough room on my board before we actually transmit the 90 again. So we're going to have full loss of transverse magnetization before we do that again. And then it's going to be the 90 pushing more longitudinal magnetization into the transverse plane and not refocusing any transverse magnetization.
As a class, when will we be getting into that?
Into what?
Of what you just talked about?
We'll talk more about that in physics too.
Physics too. Okay, got it.
I like the question. It's the same questions I asked, and I started seeing the breakdowns of all the models, but it's hard to really understand it that way when when you start asking those questions that deep.
The only reason I asked was just because we were talking about the idea that the T2 decay is non-recoverable, and so I was just trying to get a deeper understanding of exactly what that meant. But you just mean for this model, we're talking about the idea that T2 is non-recoverable.
Yeah, T2, yeah, until we completely lose transverse magnetization. So think about it kind of like this. Off of my first longitudinal flip, that has to fully decay. I can flip other longitudinal magnetization into the transverse plane once it starts to recover. I can also refocus the transverse magnetization that's decaying, but we have to allow for longitudinal recovery to exist before we can flip that back into the transverse plane. So if I were
Yeah,
to
that's what I was thinking.
excite and refocus, there'd be nothing to really push back into the transverse plane until I wait a certain period of time.
And on the last bullet point for that slide, it says the 180-degree refocusing pulse cannot eliminate true T2. When you say eliminate true T2, you just mean the whole like T2 decay process.
Yeah,
Right.
so notice we're getting a lower amplitude echo every time.
Yeah,
It is not refocusing the FID all the way back to 100%, right?
got it.
And the reason for that is true T2 decay is going to continue to happen. So the signal is going to be continuously less and less, even when we do refocus it. And that loss of signal over time is not going to be compensated for by the 180-degree refocusing pole.
Got it. Okay. All right. Thank you.
You're welcome. Y'all want to take 10 minutes before we continue? All right. Let's come back at 11:50. Please, if you have any questions when we come back,
Okay.
let me have them.
11:50 or 10:50?
10:50, sorry.
Oh, you're good.
All right. Would anyone like to revisit any of this that we've already discussed? All good to go, huh? All right. Let's move along then. A little review. Talked about this already, but our timing parameters, literally adjustable as an MRI technologist. You can you input these parameters into the graphic user interface, and the images come out in different ways with different contrast based on these numbers that you put in there. Fortunately, like, the computer will save the numbers, so protocols are typically built already, but you can make changes. They're all adjustable, and sometimes they do need to be adjusted. So, once again, 90 degree, 180, followed by the echo. Exactly one half of this echo time is when the 180 is transmitted, and that should make sense, right? Because the amount of time it takes to the amount of time you're allowing for dephasing to occur is the same amount of time it's going to take after you flip them 180 for rephasing to occur, right? So if we select a TE of 30, let's say this TE right here is 30. When is the 180 transmitted after excitation? 15, right? These are milliseconds. So if I have a TE of 30, then the 180 is being transmitted exactly one half of that time. That makes sense? Yeah. So what are our timing parameters? TR, standing for repetition time. It's the time from one RF excitation pulse to the next. This is a little bit deceiving because, we're typically, if we were looking at a to scale diagram of this, the 90 would be way out in front, much further than the echo time. TRs are going to be much longer than TEs, essentially. But just to fit it on one page, this is how it ends up being. But I would say it'd be more like this. This is your TE, the TR would be way out here somewhere for if you wanted to make it more to scale. This controls the amount of T1 weighting we see on an image. Right, we've already memorized this, but we're going to talk about why. So remember, T1 once again is the longitudinal recovery time, right? So if we're going to get T1 weighting, we're going to exploit the differences of longitudinal recovery times between different tissues. Okay. TE, it's our echo time, our time from the 90 degree to the center of our echo, to the middle of the echo. The echo always occurs at a time that is double the time between the excitation and refocusing pulse. So 180 is at one half of your TE, and this controls the amount of T2 contrast that we see on an image. So when we are weighting something to be T2 weighted, we are exploiting the differences between the different T2 times, or the different transverse decay times between different tissues, to give us contrast. People get confused though. They think in a T1 weighted image, I don't prescribe a TE. And in a T2 weighted image, I don't prescribe a TR, but that's not true. TR and TE are prescribed in every image weighting, right? So if I have a T1 weighted image, I have to have a TR and a TE, and vice versa. If I have a T2 weighted image, there has to be a TR and a TE as well. They work together to determine how much T1 and how much T2 contrast we see on the image, or information, T2 and T1 information we see on the image. They need to be used correctly so that we weight the image towards one contrast or another. Going back to what I was saying before. So in a T1 weighted image, do I have to prescribe a TE?
Yeah.
Yes. I prescribe a TE, though, that minimizes the amount of T2 contrast that I see. Right? And in a T1 weighted image, I'm going to prescribe a TR that minimizes the amount of T1 information that we see. That makes sense? And then in a proton density weighted image, I'm going to minimize both T1 and T2 contrast so that I see just contrast based off of only the differences in the amount of protons are within each tissue. Here are some T1 and T2 times of different tissues. You're going to find different numbers out there. This is sort of just as a model to kind of demonstrate a point. What do you notice about the differences between T1 and T2 times of the same tissue? So if we look here, gray matter, it has a T1 time, or the time it takes for 63% of its longitudinal recovery to occur, right? It's at 900 milliseconds. Its T2 time, the time it takes for 63% of its transverse magnetization to decay to where there's 73% left, is 90 milliseconds. What do you notice about the T1 and T2 times of any given tissue?
T2 is much faster.
Exactly. T2 decay happens much quicker. So dephasing based on spin-spin interaction is going to happen much quicker than that recovery of the longitudinal magnetization. Y'all agree? T1 times are longer, much longer in most cases than T2 times. Therefore, longitudinal recovery, T1 recovery, takes longer to occur than transverse decay or T2 decay. This property will be reflected in the TR and TE times selected to get the desired contrast of an image. My point in saying this is that when we talk about a long TR versus a long TE, the long TR is going to be much longer than a long TE. We might call a long TR might be 3,000 milliseconds and higher. A long TE, on the other hand, might be something between 80 and 120, right? So both of them are considered long, but a long TR is much longer than a long TE. And this is reflected because of the fact that, or this exists because of the fact that T2 happens much faster than T1. Look at the difference between ice and the T1 and T2 times. I've never imaged ice before, but I kind of want to now to see if that's actually the case. I do know somebody who used to image cadavers. I don't know if they were frozen, so I'm not sure how much ice there was in there, but they stayed really still. There we go. Someone's paying attention. All right. So here we go. How does this work? T1 relaxation and TR. Remember, what controls T1 recovery or T1 weighting? TR. And to get T1 weighting, we want to prescribe a short TR. Write that down. T1 weighting is achieved by prescribing a short TR. A short TR means that RF excitation pulses are going to be applied in rapid succession, right? All that's saying is that one excitation pulse is going to be followed by another one very quickly, right? If that happens, which it does in a short TR, full longitudinal recovery cannot occur for tissues that take a long time to do so. Right? So for tissues like water and ice, they are not going to be able to recover very fully if I prescribe a short TR, right? Yes?
Mm-hmm.
All right. Therefore, because they don't fully recover, these tissues will become saturated with energy. Because remember, T1 recovery is a loss of energy, right? It is energy to the lattice, spin lattice relaxation. So if they are saturated with energy, they will produce low signal because longitudinal magnetization is a determining factor of subsequent transverse magnetization. Remember, I have to have somewhat of a longitudinal component before I can have a transverse component, right? So this is going to flip into this. This is only going to flip into this, right? So we need some sort of substantial longitudinal magnetization to then flip again into the transverse plane. If we excite quickly, so here's the first excitation pulse. Water and fat, boom, first excitation, it's all in the transverse plane. We're not going to worry about the transverse magnetization though at this point. We're going to wait for recovery to happen. Why there's a head by me? Do you see that? Or a hand by my head?
I mean,
Somebody has a question.
Who's got a question? Oh wait, that's me. I raised my hand. I guess I just did this. Interesting. All right. So first excitation pulse. Fat and water, they go into the transverse plane. Right? We're not worried about that though. We're going to wait. Which one's going to recover back longitudinally faster? Fat or water?
Fat.
Fat, right? It has a quicker T1 recovery time. Fat is going to take longer, right? If we excite again quickly and not wait a long period of time, let's say we wait 400 milliseconds and we excite again, boom. Which one has more transverse magnetization after that second excitation pulse?
The fat?
Fat, right? And then if we measure back that signal very quickly by refocusing and then listening back at a short TE, we will now have contrast or differences in signal intensities based on the differences in T1 recovery times. Right? So, let's say this is water. Excite, boom. We allow for a small period of time for longitudinal recovery to occur. Water takes a long time to recover. We excite again. Water will not produce a lot of signal, right? On the other hand, tissues with a quick longitudinal recovery time, fat, boom, we excite, it recovers back quickly. We excite again, will produce a lot of signal because it is not saturated with energy because it's able to release its energy back to the molecular lattice because its molecular tumbling rate closely matches the Larimar frequency. Thus, it has a quick T1 recovery time. Therefore, these tissues with quick T1 times will produce high signal. So with a short TR, we have contrast of tissue based on T1 relaxation times, known as T1 waiting. So here we go. Water, blue arrow, takes longer to recover than fat. So we excite. We're not listening back to an echo on this first one. We have to prepare the tissues. So we don't collect an echo after the first TR in a T1 weighted image. In a short amount of time, fat recovers longitudinally much faster than water does because it has a quick or a long T1 time. Does fat have a long T1 time or a short T1 time?
Or
Short. It recovers fast, right? So it's going to recover longitudinally much faster. In a short amount of time, when another excitation pulse is applied, water, being saturated with energy, doesn't produce a lot of transverse magnetization. But fat, having almost fully recovered, will produce a lot of transverse magnetization. Now we have differences in signal intensities when we collect an echo, allowing fat to produce high signal and water to look dark, giving us contrast. Contrast based on T1 recovery times. Yes?
that's because the water flip angle is like further away from 90, right? Compared to fat.
No, don't worry about these components right here. Just think about this longitudinal component. It's flipped 90 degrees, right? Don't worry about this piece right here. Just think about this longitudinal component becoming transverse magnetization. The transverse component of magnetization is what is producing our signal. So you can see how this small longitudinal component after a 90-degree flip becomes a small transverse component.
I have a
And this
question.
large longitudinal component becomes a large transverse component. Yes, I heard somebody had a question.
Yeah, imaging wise, if it's saturated, does that mean it'll be darker? Like the image will be darker?
Correct. If it's saturated with energy, it doesn't have a large longitudinal component to flip into the transverse plane. Thus, it does not look bright. It will look dark.
Thank you.
You're welcome. Let's take a look at this video.
Down into the longitudinal axis.
So two different tissues here. Don't worry about the T2 decay times. We're only interested in the longitudinal recovery. We do have to negate dephasing, and we do that by listening back to the echo or creating a short TE or prescribing short TE. But the contrast comes from the short TR and not
Transverse plane.
allowing for full longitudinal recovery.
We've given them identical T2s because we can, because it's graphics. So they decay away at the same rate in the transverse plane, but we've given them different T1s. So in this sample, we've given the yellow tissue a rapid T1, a short T1, and the green tissue a longer T1. So what would happen if instead of waiting for these things to remagnetize completely, if we put another excitation pulse into the system now? Well, this, and I don't have a graphic example, is the yellow vector would project down the same size it is here, and the green one would too. And when we then measured the signal, the yellow vector would give off approximately twice as much signal as the green vector. And we'd be able to discriminate between these two tissues based on their different T1 relaxation rates. Okay? So to get a T1...
You didn't finish right there, but to get a T1 weighted image, we need to prescribe a
Low TR.
short TR. We need to not allow for tissues that have long T1 times to fully recover, right? So it should be as simple as this. Without longitudinal recovery happens at different rates. We have to have longitudinal magnetization to create transverse magnetization. So if we excite and we wait a short period of time before we excite again, tissues with quick T1 times are going to recover and have a larger longitudinal component than tissues with very long T1 times. Once we excite again, we will now have the tissues that had that short T1 time producing a lot of signal. The other tissues that have a long T1 time will not produce a lot of signal because they are saturated with energy and unable to flip longitudinal magnetization into the transverse plane. So let me ask you this question. What type of tissues, based on their T1 times, look dark in a T1 weighted image?
Ones with long tear times.
With a long T1 time. Tissues that take a long time to recover longitudinally. Therefore, the tissues that look bright on a T1 weighted image have a quick T1 time or recover longitudinally very fast. So if I want T1 contrast, what do I need to do?
Do a short TR.
I need a short TR. If I want to eliminate T1 contrast, what do I need to do?
Increase the TR.
Increase the TR. So look, however, if we wait a long period of time between successive RF excitation pulses, fat and water will both have time to fully recover longitudinally, right? So if we excite and then we wait and then we keep waiting, eventually both of them will fully recover, right? And then when we excite again, they both are basically giving the same amount of transverse magnetization, right? Because they both had time to fully recover. So if I want to eliminate T1 information, I need to prescribe a long TR to allow for all tissues to recover fully in the longitudinal plane.
Just to reiterate, so I can get this down correctly. The short TR equals lighter contrast in the image.
A short TR gives us better T1 weighting, gives us T1 contrast.
Thank you.
A long TR will eliminate T1 contrast. But you have to know why. Understanding that something happens because of something else is part of the story, but you need to know why. Why does a long TR eliminate T1 contrast?
You're allowing all the tissues to recover, so now you can't really like differentiate and get like a stronger signal from one or the other.
Yeah, so we're allowing for full T1 recovery to happen. So now when we flip again, any sort of contrast will not be based on T1 recovery times, right? Because they all fully recovered. We can see here there is a difference, right, between the size of the transverse magnetization of fat and water, right? But that's how it was to start off with. That just means there's more water here than there is fat to begin with, right? So that contrast.
This will basically make the this will basically make this the middle picture in the first slide, right? That we talked about. Don't that have like no like contrast at all?
This is no. Well, yeah. This would be proton density. Yeah, you're right. If we allowed for full longitudinal recovery, excited and listened back right away, then yeah, it would be proton density weighted. That is correct. So now that we all have that 100%, let's talk about T2 relaxation and TE. Sorry. To get T2 contrast, we need a long TE. And what does a long TE mean again? It means a long time between excitation and when we listen back to the signal, which means it's a long time between excitation and refocusing, right? Because that's 1/2 of the TE. If there was a longer period of time between RF excitation pulse and when we collect the echo, a large amount of transverse decay will happen to tissues with short T2 times. Right? Some tissues are going to decay much faster in the transverse plane. I'm going to ignore T2 star now. Just think about it. It's happening, right? T2 star is happening. I'm just going to take that component out of it to make it easier to understand. Excite. Some tissues are going to have much quicker T2 decay times than other tissues. If we wait a long period of time until we listen back or collect the echo, tissues with short T2 times are going to look what?
Dark.
Dark. Tissues that hold on to their transverse magnetization for longer and have a long T2 time will thus look bright. Again, we have contrast, right? That contrast now being based on the transverse decay rates as opposed to the longitudinal recovery times. Right? Tissues with short T2 times, such as fat, that lose their transverse magnetization quickly will produce low signal. On the other hand, tissues with long T2 times, such as water, holding on to their phase coherence for longer will produce a lot of signal because they are holding on to their transverse magnetization that is cutting through the coil of wire. So now with a long TE, we have contrast between tissues based on the differences in their T2 relaxation times. This is known as T2 weighting. So how do we minimize T2 weighting?
Short T.
Short TE, right? We excite, and then we listen back right away. We excite, we refocus, we listen to that echo before any true T2 or as minimal as possible T2 interactions happen. Right? So if we excited, refocused, listen back to the echo, that would be absent of T2 information. We excite, we allow for a long decay time, we refocus, listen back. Now we have differences in signal intensities based on T2 relaxation times, also known as T2 contrast. So here we can see these are the T2 decay times. The dephasing of water happens much slower than the dephasing of fat. Fat has much closer packed molecules, so the hydrogen is much closer together. The magnetic moments have much more of an effect on each other in fat than they do water. In a relatively long amount of time, when we listen back to the echo, with a long TE, water has phase coherence still and is producing signal. While fat has been dephased almost completely and is not producing much at all. Now we have bright water and dark fat, known as T2 weighting. Bright fluid, dark fat. Bright fat, dark fluid. On the other hand, if we have a short TE and we listen back to that signal right away, there's not going to be much difference in the transverse components of magnetization, right? Both fat and water will have phase coherence in a short TE and both produce a lot of signal. Does that give us T2 contrast? It does not. The signal intensities will be based on the amount of protons in each imaging volume. That's proton density right there. We can see the difference between a short TE and a long here.
Excited, they get out of phase, signal diminishes if we were to measure it, flip them over, and if we look at what happens with short echo time, they're almost perfectly in phase, but not quite. And we'll explain why, or I'll explain why that happens in a minute. They get out of phase, and the signal goes away. If, on the other hand, we wait a longer period of time after we tip it from its resting state, we wait, they get more and more out of phase, and then we refocus it with a pulse which is stronger. When they come back together, they don't come back together as well. So we get a smaller echo. And the reason they don't come back together again is even though this gets rid of the inhomogeneous effects which are spatially distributed due to the inhomogeneity in the magnet, it does not take care of the effect of how one proton affects the other. That's called spin-spin coupling. It's not a reversible effect. So the echoes keep getting smaller and smaller, and we get that. And if we draw a curve from the origin to the peaks of each of these echoes, that decay is called T2.
So that was more just showing you the actual spin-spin interaction decay, but related to T2 contrast. So how do these work together? Remember, like I said, TR and TE are both going to be in every single image weighting. We have to prescribe a TR and a TE, even if it's T1, T2, or proton density weighted. So for T1 weighting, we want to have a short TR to maximize the T1 contrast, right? To not allow for full longitudinal recovery on all tissues, particularly the tissues that have a long T1 time, right? But we also want to prescribe a short TE because we want to listen back quickly before we get T2 dephasing. Because remember, both of them are happening independently, but at the same time, at different rates. So let's say we excited once, we have recovery, we excite again, right? We want to listen back right away before this starts to decay, right? Because if we start getting decay in the transverse plane, we're gonna have no signal and no contrast again. So for T1 weighted image, we want to have a short TR, boom, and then we want to listen back right away, or a short TE. What does the short TE do for us in a T1 weighted image? If you can answer that question, you're going to be doing well.
It decreases the T1 contrast.
Anyone else want to give it a shot? What does the short TE do for us in the T2 weighted or in a T1 weighted image? First of all, what does TE control?
T1 contrast.
Nope.
I mean, T2
T2.
contrast.
Yeah. So what does having a short TE do for us?
It increases the T2 contrast.
Short TE decreases T2 contrast. And that's what we want to see in a T1 weighted image. We don't want to see T2 information. Why do we have a long TR in a T2 weighted image? What does TR do?
It increases T1 contrast.
Minimizes T1 contrast.
By allowing for full longitudinal recovery, right? So we want all tissues to be fully recovered before we excite again. And that minimizes the T1 contrast, right? So for a T2 weighted image, I want a long TR to minimize T1 contrast. And then I want to wait a long period of time before we listen back to get T2 contrast, or contrast based on the differences in T2 decay rates. You're going to have to know which tissues look bright and dark in different weightings and why, and how we would change that. So for proton density, I'm going to minimize T1 contrast by allowing for full longitudinal recovery. And then how am I going to minimize T2 contrast? By listening back to the echo or recording the signal right away before T2 decay can happen. So for proton density, I will have essentially all the protons recovering, long TR, and then listening back right here. So no T1 contrast, no T2 contrast. I'm just going to have contrast based on the sheer amount of protons are in each given tissue. There can't be no questions.
I have questions. I just don't know how to articulate it properly.
We'll take a minute and think about it. You guys are going to have to know these parameters so that we can play this game here and understand what's going on. These are all just tools to understand the concepts here. Short TR, anywhere between 350 and 800 milliseconds. That is considered a short TR, generally speaking. It can go outside of that sometimes, but for our purposes, this is what we are going to say is a short TR. So T1 waiting, short TR, going to be 350 to about 800 milliseconds. A short TE will be considered 0 to 25. The reason I say minimum to 25 is because 0 is impossible, right? We have to refocus and get rid of the dephasing due to inhomogeneities and susceptibilities, right?
Yes.
That takes time. So we can't have a TE of 0 at this point. We have to allow for that decay to happen and then refocusing. But if we do it very quickly, we can usually, I mean, I've seen it down in, on a spin echo sequence. I think I've seen the lowest TE be around like 5 milliseconds or so. You can get lower for gradient echoes. Once again, why do I have a short TE?
To minimize T2 contrast.
Minimize T2 contrast, thank you. And why does that minimize T2 contrast? Doesn't allow time.
Doesn't, I don't have
Tissues to dephase. Doesn't allow time for T2 interactions to happen between different tissues. Thus, it doesn't give us T2 contrast. And then it's a 90-degree flip angle and 180-degree refocusing pulse. That's just telling us that it's what type of pulse sequence? A spin echo pulse sequence, right? And the reason this is important is because the gradient echo pulse sequence is going to have different parameters as far as flip angle and refocusing. T2 waiting. We have a long or short TR.
Long.
Long, right? That's going to be, we're going to say 2,500 milliseconds and up. If I keep waiting, does it matter? Once I hit full longitudinal recovery, am I going to get any further than that? No, so I can keep waiting. It's not going to affect my contrast at all. It'll affect your scan time, not your contrast. Also, a long TE. A long TE for our purposes is going to be somewhere between 80 and 120 milliseconds. What happens if I go below that? What if I select 30 milliseconds?
You're
What is
not going
that
to see much.
long- Sorry, go ahead.
I was just gonna say you're not gonna see much contrast between or variation between the different vectors.
Yeah, because you're not going to have a lot of T2 decay happening, right? So if I select something that's lower than what I have here, we're not allowing for much contrast, right? Because we're not allowing for enough time for T2 interactions to happen, giving us the contrast we desire. Exactly.
Wouldn't that be proton density?
Yes, it will be more proton density weighted at that point. So if we want T2 contrast, we have to have that long TE. What happens if we wait too long?
No signal.
There we go. Everything goes away, right? And once again, the 90-degree flip angle, 180-degree focusing poles. Proton density, long TR. What's a long TR, everyone?
Over 2,500 milliseconds.
There we go. What does that do for us? Why do we want a long TR?
Trying to minimize the T1 weighting.
Yep. You take my T1 and get rid of it. And how is it getting rid of? It's by allowing for full T1 recovery to happen. What do we want our TE to be? 0 to 25, right? We want to not allow for T2 decay to happen. And what does that do? Minimizes our T2 contrast. What are you thinking? What kind of weighting do I have there?
U1.
T1. Why?
You have the short TR and short TE.
Yep. TR, not allowing for longitudinal recovery, full longitudinal recovery for all tissues. TE, not allowing for much T2 decay, minimizing T2 information. What do I got?
U2.
Sure about that.
Proton density.
Wait, no, yeah, proton density.
TD, I've eliminated T1 information. I've eliminated T2 information. What do I got now?
Now it's T2.
Now it's T2, right? Eliminated T1 information. Maximize T2 information. What do I got now?
That's
Is there just no contrast?
I just messed up my scan. That would be signal poor. That would look like nothing. I'm not allowing for full recovery, so water's already not going to produce a lot of signal, and then we're going to allow for fat to decay. It's just going to look like, it's going to look signal poor, like basically like nothing. That's improper parameters right there, right? That's giving us T1 contrast and T2 information, right? We can't mix the contrasts. Let's watch this video real quick. Does anyone have any questions? I feel like I'm not getting nearly enough interactions here. Everyone doing okay?
Just the T1. Well, I don't really know how to ask. I'm just like I gotta go over it again
Okay.
on the PowerPoint slides. That's all. I'm just not really understanding the just the time, the milliseconds between T1, T2, and the PD, and just how to associate between the three. And
Yeah.
just like
Well, your key is right here. If you want to just memorize numbers, this will help you a lot.
it's like the numbers, but then also just like how it affects the different tissues and like what I'll get back in terms of contrast. Like like how the like the spin echoes for the refocus pulse and like just all that, like what I'll pretty much what I'll get back in terms of an image. I just want to like be able to configure that with the TR, TE, T1 relaxation, T2 relaxation, and all of that. So,
Yeah, it's important to understand why it's happening. So you got to break it down like I have for you into
yeah.
each individual component. What is a short TR doing? What is a long TR doing? What is a short TE doing? What is a long TE doing? What are the mixtures of those doing? Right. So let's go ahead and watch this video and see if this helps at all.
Thank you.
Because these protons in our bodies have different local environments, some associated with the free-flowing water molecules, while others are fixed in position associated with the structural or energy-storing molecules of protein and fat, Because these protons in our bodies have different local environments, some associated with the free-flowing water molecules, while others are fixed in position associated with the structural or energy-storing molecules of protein and fat, they have characteristic differences in their T1 and T2 relaxations. We can accentuate and measure these differences by changing how quickly we put in the radiofrequency energy, or the repetition time, designated TR, and how quickly we choose to listen to the signal coming back from the transverse magnetization, or echo time, designated TE, of the precessing protons. This process is referred to as the pulse sequence, and we will use a sample of fat and water to demonstrate these differences.
Just so you know, for simplicity's sake, he is not going to introduce the 180. When he says, listen back to the signal, just think about it like right in the middle of that, there's going to be a refocusing pulse. It's just left out of the equation for simplicity's sake.
As before, to simplify and maximize comprehension, we're going to stop the precession of the protons. On the left is a group of spins or protons associated with fat, and on the right, water. When we put in our resonant radiofrequency pulse, all the protons absorb that energy, flip into the high energy state, and spin together to produce our 90-degree pulse or transverse magnetization. If we wait a sufficient amount of time, the protons will move apart in a T2 or spin-spin relaxation, and the transverse magnetization will decay. The protons associated with the free fatty acids, being relatively fixed in position, decay rapidly as the spins push away from one another. They also give up their absorbed energy more rapidly as they fall back to baseline in a T1 or spin lattice relaxation, depositing heat energy into the surrounding tissues and regrowing the longitudinal magnetization. On the other hand, the protons in the freely flowing water can hold on to their energy and continue to spin together in phase, thus maintaining the transverse magnetization. At this point, when we turn on our receiving coil and measure the signal coming back from the protons, the relatively large transverse magnetization in water will give a strong signal, while the smaller or absent transverse magnetization in fat will give a weak signal. By convention, the strong water signal will be assigned a grayscale color of white, and the weak signal of fat will be dark gray or black. Hence, to accentuate the different T2 relaxations of the protons in our bodies, we would wait a long period between radial pulses, referred to as a long repetition time TR, and wait a long time to listen for the return signal or echo, referred to as a long echo time, TE, and these differences can be measured and recorded. Using these same tissues in their baseline state to accentuate the differences in T1 relaxations, we again put in our 90-degree resonant radio frequency pulse, which flips the protons into the high energy state and pushes them in phase to produce our transverse magnetization. T2 relaxation occurs as the protons move apart, faster in fat than in water, and then the protons fall back into the low energy state, dissipating the absorbed energy as heat into the surrounding tissues and regrowing the longitudinal magnetization. Again, because the protons in water are fluid and move freely, they tend to hold on to that energy longer, and the protons stay in the higher energy state with little regrowth of the longitudinal magnetization, whereas the tightly packed fat protons more rapidly give up that energy and return to the low energy state, thus rapidly regrowing the longitudinal magnetization. If we then quickly put in another resonant 90-degree radio frequency pulse, the fully recovered fat protons will produce a large transverse magnetization and a strong measured signal that we can record if we listen to the return signal or echo shortly after the second radio frequency pulse. However, the water protons are still in a high energy state with little regrowth of the longitudinal magnetization. Therefore, the new radio frequency pulse flips more of the low energy protons into the high energy state and can only produce a small transverse magnetization as well as a net longitudinal magnetization oriented 180 degrees or directly opposite the main magnetic field. This configuration in the water protons will give a low amplitude or low energy wave when we listen for the echo or return signal. In other words, the protons in the water are saturated with energy and can no longer produce a strong transverse magnetization. Therefore, to accentuate the differences in the T1 relaxations between the protons in fat and water, we want to rapidly put in our resonant radio frequency pulses, or a short repetition time, TR, and quickly listen for the return signal or short echo time, TE. Now this is a difficult concept and you may have to listen to it a few times to get it to sink in, but to summarize, the T1 relaxation effects are accentuated by rapidly exposing the protons to radio frequency energy and keeping the spins in the high energy state and thus reducing the effective longitudinal magnetization. Tissues that recover quickly will have a large signal, while those slow to recover will have a low signal. T2 effects, on the other hand, are accentuated by a prolonged echo time to allow the spins to move away from each other and accentuate the differences in T2 relaxation between regional tissues or chemicals. So a T2 weighted image is obtained with a pulse sequence of a long TR and a long TE, decreasing the T1 effect with the long TR and enhancing the T2 effect with the long TE. A T1 weighted image, on the other hand, is obtained with a pulse sequence of a short TR and a short TE, enhancing the T1 relaxation and minimizing the T2 effects. In between these two is the proton density pulse sequence, which is obtained with a long TR and a short TE, effectively minimizing the T1 and T2 effects, and basically giving us an idea of the absolute number or density of protons in the region. The first to propose the
Sorry, I'm trying to get it to. There, right there, there we go.
Now this is a
How many of you feel like that?
It's a pretty good video. So, just so I can kind of, I'm a little confused still, but just to wrap my head around the T1 and T2. T1's when the, and correct me if I butcher it, is when after the excitation pulse, that's when we start recording and the signal. And then the T2 is when we have the echo and we listen back for the signal, and we have to use on the spin echo, we have to use a refocus pulse to get the T2 contrast.
We're always using a refocus pulse. We always have a TR and a TE. Let's take it offline. We can talk, just me and you, afterwards about
Thank
it.
Okay.
Anybody else have any questions? I want to take a little bit of a break before we go into the next part. All right. It's okay to feel like this guy right here.
That's, yep.
We'll get it. All right. Let's take a lunch. We'll do half an hour. See you at 12:15.
Okay.
Thanks.
All right. Hot.
All right. Should we get back to it? And ask a question real quick. See if you can answer it, because this is the kind of depth you'll need to understand this stuff at. What is the reason that water looks bright on a T2 weighted image?
Because it has a quick recovery time. I mean, because it's, wait, no. It's a bit- the question is, why does water look darker on a T2 image?
Oh, it's why does water look bright on a T2 weighted image?
Because it has a longer longer
T2 relaxation.
TT time.
It has a long TR.
No tissue has any TR or TE. Tissues have T1 and T2 times.
Relaxation time, right?
Yeah, it has a long T2 relaxation time. And on a T2 weighted image, the second part of that answer is on a T2 weighted image, we're prescribing a long TE, meaning we're taking a long period of time after excitation to record the echo, meaning that a lot of T2 interactions are going to happen, a lot of dephasing is going to happen. So only tissues that take a long time to dephase, also known as tissues with long T2 times, will still have phase coherence and appear bright, produce a lot of signal, and therefore appear bright. There's going to be several questions about parameters and what kind of weighting is being achieved by each of these parameters. Why does fat look bright on a T1 weighted image?
Because it has a quick longitudinal recovery time.
There we go, that's part of the answer.
And
T1 has long or short TR?
it has a shorter TR. And because it has a quick longitudinal recovery and it has a short TR.
T1 weighting has a short TR, meaning that we are going to transmit RF into the tissues repeatedly in a short period of time. So tissues that take a long time to recover longitudinally will get saturated with energy and not be able to produce a lot of signal. Tissues that recover quickly will not be saturated with energy. They'll have a large longitudinal component of magnetization to flip back into the transverse plane, even when we have very short energy transmissions or excitation pulses. So I'm going to go into this other concept right here before we get into gradient echo and what a gradient echo is, and then also the contrast on the gradient echo. Don't worry if you're not completely understanding this, but it's just a good spot to kind of start to introduce it. Image data collection. Many echoes must be collected to create one image, and one image is known as a slice. So when we're looking at pictures, we call them slices. We take several slices, typically through different pieces of anatomy to diagnose, right? Maybe like 30, 40 through the brain axially. It depends on the anatomy and how thin your slices are. But each one of those slices, we have to collect several echoes to create an image. So that's why we have many TRs and many TEs, right? We have excitation, refocusing, we collect the echo, we repeat it. Do it all again. Do it all again. Each one of these echoes is put into K-space, and we have to fill all of K-space with several echoes to generate one image. So typical amounts of echoes need to be collected: 120, 220, 128, 224, 256, 320, 512. On newer systems, that's a little bit more. You can change that a bit more. It's typically going to always be an even number because K-space has to be symmetrical. So the amount of echoes above are going to be the same amount as the amount of echoes below. The amount of echoes is determined by something called the phase encoding matrix, and it's directly related to your imaging resolution, or how well you can define small detail on your images. We'll discuss that later in lecture 6, I believe, when we start to discuss it. Anyway, my point in telling you this is that we have to excite one slice, refocus, collect an echo, put that in K-space many, many times to generate one image. Does that make sense? Okay. A typical MRI scan will contain several slices. For an example, an average sagittal of a shoulder can consist of about 14. There's probably many more than that. That was just an arbitrary number in there. But that's a sagittal of the shoulder. There's probably closer to like 28 in there. But we just put 14 on here just to get some numbers. This is a K-space right here, or a representation of K-space. It's actually just a diagram of K-space. K-space actually looks a lot different than that, but you can see these are all different echoes, different lines are different echoes that are phase encoded differently until we fill K-space. So all the echoes are stored in something called K-space. Prior to image construction, we'll talk about that more later. Each slice has its own K-space. So every single image, so let's say we had 14 sagittal images through the shoulder, there would be 14 different K-spaces, each one of them containing several echoes, which depends upon the phase matrix.
So each little slice on that right there is that's the multi-slice acquisition, right?
We'll talk about that in just a second, but each one of these slices is a different image that we're planning through the shoulder here. And each one of those images
has
its own K-space. And each K-space has many different echoes to generate it, or to generate an image.
Do the echoes never mind.
Each echo is literally an echo that we collect with a particular TR and TE to generate the contrast that we desire.
I was gonna ask you. Go ahead. Sorry. No, it's okay.
All right. If each slice needs 224 echoes, meaning that the phase matrix is 224, collected to reconstruct the slice, then there are 14 total slices, then we have to collect 3,136 echoes to finish the entire sequence, right? So some simple math, 14 times 224 essentially, right? Only one echo per slice is collected per TR in a spin echo sequence. Right? So I'm not collecting any other echoes per TR. Collecting one echo per slice per TR. You can start to see how time consuming this process would be depending upon the length of our TR, right? TR is a time parameter. It does take us a certain amount of time until we go again. And if we have to go again several times to generate an image, it's going to start taking time. That's why MRI is typically one of the longest imaging modalities to achieve the entire process, all of the images needed. Fortunately, we have something called multi-slice acquisition. Multi-slice acquisition is just stating that we are going to collect one echo per slice per TR. So our TR is going to sort of define how many slices we are allowed to prescribe throughout the entire data acquisition. So let's say we excite, we refocus, We collect the echo. And then we're going to wait, right? And then we're going to do the whole thing again. After we do this, we have all of this downtime in here, right? Where nothing's happening. So the geniuses, the engineers behind this decided, hey, that's slice 1. While it's relaxing back, why not go and excite slice 2? As soon as we collect the echo, we have room to excite slice 2 and collect its echo, right? And we have a bunch of other dead time here. We can go do slice 3. And then 4. Hopefully you can see where we're going here, right? Slice 5. And we can keep doing that. We probably have 6, 7, 8, 9. There's probably about room in this TR right here for us to excite 9 slices until we have to go back and re-excite slice 1 again. So you can see that if we lengthen or shorten our TR, it is going to affect the amount of slices we have available to us. One echo is acquired per every slice in a single TR period. Each slice receives an excitation pulse. Each slice receives a refocusing, and you collect an echo, and then we can begin the whole process again. While we are waiting for that slice to relax back as much as we want it to relax back, and then start the process again. TR and TE are going to determine the amount of slices we have available, right? Because if I lengthen my TE, I can't start my next slice until later. So in this case, let's just keep going down here. Let's say, I'm not going to do different colors, it's going to take forever. Right there, that's about as far as I can go. So I had 1, 2, 3, 4, 5, 6, 7, 8, 9 slices available to me, right? If I needed a 10th slice, what would I need to do?
Lengthen the TR.
Yep, increase my TR. Now I can fit a 10th slice in there, right? What if because the contrast being T1, I had to decrease my TR?
Less slices.
Yeah, I get less slices available, right? So you can start to see how this has an effect on us. Here's some numbers here we can put on it. Let's say we have a TR of 400 milliseconds, a TE of 20 milliseconds. To the center of the echo, let's say we need an additional 5 milliseconds to continue to listen to the echo, so that would be like a 10 millisecond echo window, essentially. That means if we do the math, we can fit 16 slices can be acquired before we have to fit the second slice in. Before we have to go back for the second acquisition of slice 1. And you can see the difference here if we raise that TR. What kind of weighting do we have here?
That's a T1.
This is T2 weighting. Long TR, long TE. 80 milliseconds the center of echo, 5 more afterwards. About 30 slices can be acquired before we have to go back and do the second excitation of slice number 1. So we can see with longer TRs, proton density, T2 weighting, we can fit a lot more slices in before we have to go back and re-excite that first slice. So there's certain things that have to be done, and you'll notice too as you're scanning, changing the amount of slices is going to change your scan time because it's going to change your TR accordingly. And you have to be careful about changing your TR because now we know it is related to contrast. And if we want T1 contrast, we can't lengthen our TR too much, otherwise the T1 contrast goes away. Just want to bring in this, excuse me. I just want to let you guys understand this principle in MRI, and a lot of techs really don't get this down, and they wonder why their scan times are adjusting when they're adding or subtracting slices, and why their TR has increased too much, and what they can do to adjust it if they need a lower a lower TR to get T1 contrast. And the reason it's happening is because this exists, multi-slice acquisition. We're always collecting at least one echo per slice per TR during the pulse sequence. Does that make sense?
So in a nutshell, the MSA is just used so we can get more echoes out of a slice. And if we increase the TR, we can get more slices, but that would affect the type of weighting we get.
Multi-slice acquisition is the engineering behind how MRI data is gathered. It is a parameter construct that we need to function under. Anytime a system is doing a pulse sequence, it is going to collect one echo per slice per TR.
Per TR.
So our
Okay.
TR is going to control the amount of slices we have available to us. And the TE to some degree. That's all that's saying.
And because of that one slide where it showed the T2 weighting, is multi-slice acquisition, it's only done with T2, right? T2 weighting
Multi-slice acquisition is done every single time.
every single time. Okay.
It is the way that the engineering of the pulse sequence is set up. It has to happen this time.
Okay. So okay. Thanks.
So that being said, a T1 weighted sequence is always going to have less slices available than a T2. There's other things we can do to account for that, though. We'll talk about later. All right, gradient echo pulse sequences. Ready to get completely confused?
Yes.
Here we go. Gradient echo. What do you notice different here?
The flip angle is variable.
Yeah, sorry. It's my COVID positive test. Everyone just say, RF transmit is going to be a variable excitation pulse. So we're not going to take all of our longitudinal magnetization and put it into the transverse plane. We're going to do just part of that into the transverse plane. Most of the time. We can do a 90, but I'm going to say, it's going to say more often than not, we do less than 90. I'm going to say 99.99999% of the time we're going to do less than a 90. Any other difference that you notice in here from the spin echo sequence?
There's no refocusing pulse.
Exactly. The gradient echo uses the gradients to create the echo instead of refocusing. And this diagram is a little bit misleading because it's not showing you the RF received before it turns into an echo, and it's also not showing you the gradients. But what do gradients do again? They create a linear change of field strength across distance, right? If I have protons processing in phase at the same frequency and I turn on a gradient, what happens to those protons across that distance? What happens to their precessional frequencies?
They process at different speeds.
Yeah, across the gradient, right? So some of them over on the high end of the magnetic field strength will start to speed up, and the ones on the low end will start to slow down, right? So it's going to cause the protons to dephase, right? Even faster than they would normally dephase. And now imagine I did that gradient, I turned on that gradient, but I turned it on equal and opposite. So now the protons over here that sped up are going to slow down, and the ones over here that slowed down are going to speed up. They're going to eventually catch up to each other, right? So what we essentially do is we create another layer of inhomogeneity, causing the protons to dephase, and then we reverse that inhomogeneity, causing them to rephase, at least to some degree. There's still T2 star effects and T2 effects that are happening, but we can generate a little echo that looks like this. So in a gradient echo pulse sequence, the FID is intentionally dephased. This would normally be the FID. Remember, T2 star decay, just dephasing it. It is then immediately rephased. Sorry, the gradient is then turned on to cause the FID to dephase even faster, right? So if we didn't put a gradient on, this would be the FID. Putting that gradient on causes it to dephase even quicker. If we reverse that gradient, we will get the protons to come back into phase to some degree, albeit within that T2 decay curve. We're not going to get a larger echo. It's still going to be within that T2 star curve. But what does this do for us? It creates an echo, which creates symmetry, right? Remember, we said we had to have that symmetry before. This grows and then shrinks, as this did not. Hopefully everyone can see that if you look in here where the mouse is. That looks like it's symmetrical, right? We have a peak, and then we have it growing to that peak and then shrinking from the peak, right?
Yeah.
On this side, we don't. So if we grab that same portion, there's no symmetry there. By turning on a gradient and then turning it on equal and opposite, we get an echo. There's another reason we have this gradient on too. It's called spatial localization. We'll talk about that later. Comparison, spin echo and gradient echo. Spin echo, the phase decayed, and then at some point, the FID decayed by loss of phase coherence due to T2 star. At some point, we decided to transmit the 180-degree focusing pulse, and then we got an echo back here. Gradient echo, we're zooming into just this piece, right? So zoom in, and this happens right within this area. So hopefully you can see the gradient echoes collect data much, 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 much faster than spin echo sequences, since it's all happening within the FID, essentially. Gradients can be applied much faster than the 180-degree RF pulse, meaning shorter TR and TE settings can be achieved. Gradient echo sequences are inherently faster than spin echo sequences. That was essentially the first reason they created them, was for speed. There's a lot of other different benefits too, and limitations as well. One limitation, or here's several limitations right here. Gradients refocusing does not eliminate T2 star, right? That T2 star is still a part of the dephasing, the amount of dephasing that occurred.
But that will never change just because it has to do with the inhomogeneities from the...
Yeah, but we can minimize it. We can eliminate that information with a 180-degree focusing pulse. Now that we're using gradients to refocus, we're not eliminating that information. So anytime we collect data, the amount of dephasing between different tissues is going to be based on T2 star effects, not just T2 effects. Therefore, the contrast is going to be called something different, but it's also much more sensitive to magnetic field inhomogeneities. Because what was T2 star? T2 star was dephasing from susceptibilities and inhomogeneities. So if we're not using a 180-degree focusing pulse, we're going to have susceptibilities and inhomogeneities affecting the image quality a much, much greater. There's also less signal because we're not tilting all of the longitudinal magnetization completely into the transverse plane. We're only tilting a piece of it. So our transverse component becomes much smaller. So less signal from the inherently less transverse magnetization. So those are the disadvantages. Take a look. What are we looking at right here?
The picture on the right is more defined than the one on the left.
Yeah, just generally, what are we looking at though?
The ICs.
Yep, those are the IACs right there. What it's pointing at. In the IACs, we have air meeting tissue. Anywhere where we have an air tissue interface, or where air and tissue meet, we get a susceptibility. There's a magnetic susceptibility right there. We can see with the spin echo sequence, it eliminates that susceptibility, so we can actually see what's going on. Not in the gradient echo sequence, though. Inhomogeneities cannot be compensated for. Why? Why
Because
can't we compensate for inhomogeneities?
it doesn't get rid of the effect of T2 star weighting.
Because we don't have a 180-degree refocusing pulse, which compensates for the dephasing due to inhomogeneities, right? Therefore, it'll also have a larger effect on the imaging contrast. True T2 weighting cannot be achieved. So when we talk about gradient echo sequences, we can't get T2 weighting. We can get T2 star weighting. Because now the differences in tissues dephasing is going to be due to spin-spin interactions, also inhomogeneities and susceptibilities. All of that is going to determine how much dephasing has occurred when we collect the echo. So we cannot call gradient echo sequences T2 weighted anymore. We can call, if it is weighted towards T2, it's going to be a T2 star weighted gradient echo. But we can still achieve true T1 and PD weighting. So how does this work? Remember, so for now, think about gradient echoes as always having a short TR. So write that down. Gradient echoes always have a short TR. That was the whole point of them, right? Short TR and short TE. So why would we have a long TR? We don't. We have a short TR consistently. If I have a short TR, does that mean I always have T1 weighting?
Yes.
But I just told you the gradient echoes can be T2 star and
T1
T weighted, right? So
T1.
they're not always T1 weighted. If they always have a short TR and they're not always T1 weighted, then something else has to control the amount of T1 weighting. And in this case, it's the flip angle. The flip angle controls the amount of T1 weighting in a gradient echo image. TR is always short. So in order to saturate tissue with a long T1 times, we have to use a large flip angle. So just like a spin echo sequence, we use a 90, which is a large flip angle, right? With a short TR, that's going to saturate tissues with long T1 times and give us T1 contrast. So with a gradient echo sequence as well, we have a large flip angle, somewhere between, let's say, 70 and 90 degrees. In 70 and 90 degrees, if we do that, just think about our longitudinal component. This is all we have left, right? Fat will relax back, and then we do it again. We'll have T1 contrast with a large flip angle and a short TR. If we only flip a little bit, let's say to 20 degrees, right? That means our longitudinal component is about this much. Within that short TR period, we're going to get full longitudinal recovery, right? So then when we flip again, we will have full longitudinal relaxation and minimize T1 contrast. So with gradient echo sequences, to get T1 weighting, we want large flip angles. To minimize T1 weighting, we want short flip angles. What does the long TR do for us in a spin echo sequence? What's the point in prescribing a long TR?
Lets us collect more slices.
That, but what about contrast? What's the whole reason for contrast to have a long TR?
It allows the longitudinal recovery, full longitudinal recovery from all the
It allows
tissues.
for full longitudinal recovery, minimizing or eliminating T1 information, right? If I have a short TR and I want full longitudinal recovery, I need to give it a head start. I need to give the NMV a head start to recover, right? So just barely flip it. It's going to relax back in a short period of time, right? We want full longitudinal recovery if we want to get rid of T1 information. So to get rid of T1 information with a short TR, we have to give our NMV a head start, our longitudinal component of NMV a head start. And we do that by not flipping it as far. If we want T1 weighting, we flip it a lot, and we keep doing that again and again to get us that T1 weighting. We also need, with our T1 contrast, besides a large flip angle, we need a very short TE, just like in spin echo sequences, to eliminate any dephasing, right? To eliminate T2 star dephasing this time. So here we go. Large flip angle, 75 or 90 degrees. We can see that if we keep doing this, we're going to saturate water. Fat is going to recover. And then if we listen back quickly, we're going to have very little dephasing time, meaning there's not going to be much signal difference between fat and water due to T2 star dephasing. So, putting that together, if you're following me, T2 star contrast, how are we going to generate that? We want to get rid of T1 information first, right? How do we get rid of T1 information on a gradient echo sequence?
Shorter flip angle.
Lower flip angle. So flip everything just a little bit, allowing for full longitudinal recovery between excitation pulses. And then what else would we want to do maybe?
Higher T.
Higher TE. A relatively longer TE to allow for maximum T2 star dephasing. So look here. For T2 star contrast, we need to allow for full longitudinal recovery, eliminating T1 information. That's the whole point in that. Right? If the TR is always short, how do we get longitudinal magnetization to regrow fully to eliminate T1 information? We do that by not flipping the NMV as far into the transverse plane so that it recovers faster. So we prescribe low flip angles. And then also a relatively longer TE to maximize the T2 star information. We want some dephasing to happen. So here we go, small flip angle, and then we will wait a longer period of time because look, fat had decayed more than water in that longer TE. I say a relatively long TE because it's going to be much shorter than what we've seen in spin echo sequences. Because remember, everything is much more condensed. It's packed into the FID. So our times, even though I say they're long, they're going to appear short to you if you're comparing them to the spin echo sequences. Let me show you some examples here. TR of 700, TE of 20, and a flip angle of 90. This is a spin echo sequence. This looks like it is a T1 weighted sequence. And then you can see here, actually, this is gradient echo. Definitely gradient echo. But we can see if we lower the flip angle, you can see how we start to see contrast between fat and fluid. This one looks a lot better. Here we go. With TR and TE remaining constant, look what happens when we change our flip angle. What's happening, just based on the way these images look, what's happening as we increase our flip angle? Just comment on the signal and the contrast.
The fluid gets a little darker.
Fluid's getting darker, right? Can anyone guess why that's happening here?
T1 contrast.
Yeah, we're saturating it, right? With the 10 degree, it's recovering. So that the next time we excite, we're going to get signal from it again. When we go to 50 degrees, it's not recovering in time. So it's going to end up becoming saturated, right? So we are getting more T1 weighting as we increase our flip angle here. We're starting to saturate tissues with a long T1 time.
And the T1, for more T1 weighting, you're just decreasing the TR and the TE.
TR doesn't change, like I said. This is gradient echo. The TR is always short.
The TR is always short.
We're changing our flip angle. We are increasing the flip angle because the TR is always short to get T1 weighting.
Okay. Okay.
And then look at here how TE has an effect on it. With TR and flip angle remaining constant. You can see as we increase that TE, we're allowing for more T2 star dephasing to happen. Look what happens though, like we can kind of see the IACs here. They've completely dephased over here, but we have much better T2 star contrast, right? Like in here, that's kind of washed out. We can see the tissue contrast difference much greater here with that longer TE, giving us more T2 star weighting. We've also sacrificed any of our IAC because of that susceptibility in that air tissue interface. So you're gonna have to like go over this several times until it sinks in. I'm sure this class is too long. Half of you stopped paying attention 2 hours ago. You have to go over this over and over again and replay it in your brain to figure out how it happens. Once you see what's happening, once you can see that what we're trying to do for T1 weighting is to saturate tissues with a long T1 time, then you can see how it works for gradient echo and spin echo. It should be pretty obvious once you grasp the concept of what we're trying to do. That's why I'm always trying to get you to understand concepts and not memorize information, because memorization can only go so far. Once you start to understand that for a T2 weighted image, we want certain tissues to dephase and not produce signal, and other ones that hold on to their phase coherence for longer to hold on to it. That way, when we listen back to echoes in long periods of time, those tissues with short T2 times will look dark, and the tissues with the long T2 time will look bright. Once you start to understand that, all of this should make sense. You just have to really understand what we're trying to do here. And then the gradient echo will make sense because the TR is always going to be short. We just have to do something else to determine whether or not saturation occurs. Saturation doesn't occur when there's a short TR if we have a lower flip angle and we give a head start to relaxation. Saturation does occur with a short TR just like it would in a spin echo sequence by transmitting a large flip angle or a high flip angle. Go ahead, Max.
So back to the where was it? It was the knee, the sagittal of the knee. So they're both gradient echoes because the TR is short as well as the TE, but I'm just confused as to I thought I think I have it backwards. Would the larger flip angle make it clearer, or is just because the more times we
with this long TR, when that large, you want a large flip angle with a longer TR. It's just showing, this one's showing you there's less signal, essentially. This is a relatively long TR for a spin echo sequence. So this longer flip angle, we're going to be saturating water. I guess this one's kind of showing you, look, we can see fluid in here more now that we had a lower flip angle. I don't see any fluid, any synovial fluid in here. It's kind of darkened, but in here you can see it a bit better because of that. We're allowing for it to relax longitudinally because we only flipped it 30 degrees.
Okay, so
Saturating the tissue, saturating fluid in this one, not saturating it here.
okay. So the more times we pretty much a gradient echo, we flip it multiple times.
All of them we do. Gradient, spin
Gradient.
echo. We have to remember we have to collect several echoes, several hundred echoes for each slice. So we're doing this TR, TE, TR, TE. We're doing it many, many times. Excitation, refocus, collect an echo. Excitation, refocus, collect an echo. Those timing parameters are TR or TE. We
And
go
that's
through that time repeat hundreds of times to generate one slice, to collect the data to generate one slice.
and that's what the multi-slice acquisition is. It's just the constant repetition of those echoes and
So
recording the
multi-slice
data.
acquisition is the fact that we're doing many within one TR.
Then one TR. Okay.
Many
Okay.
slices within one TR, but we have to go through several TRs per slice to collect enough data to generate one image, right? Depending upon the resolution we desire.
Okay.
You're going to have to memorize this. T1 contrast in a gradient echo sequence. TR, it's always short. Let's just say anywhere under 800 if you need an actual number. TE as low as you can get, right? We don't want any dephasing to happen for a T1 weighted image. We don't want T2 star in there. So how do we eliminate any sort of transverse decay? We collect the echo back as fast as possible, right? With a minimum TE. Because the TR is short, we want a large flip angle to saturate tissues with long T1 times. So between 70 and 90. What kind of weighting do we have there? First of all, what type of pulse sequence is it?
T1.
Yes, it's T1 weighted. It's a gradient echo, right? How do I know it's a gradient echo?
Because there's no refocus pulse.
No refocus pulse, and it's a lower flip angle than 90, right? So it's a gradient echo, and it's high flip angle, low TE, right? So it is T1.
So that's a GRE T1. Okay.
T2 star contrast. Short TR again, doesn't really matter. TE now, it's going to be between 20 and 40 milliseconds. That's relatively long in the gradient echo world, right? Flip angle between 5 and 25 degrees. How do I turn this into T2 star gradient echo sequence? Give me some parameters.
Increase your T.
What?
Increase your T and then decrease your flip angle.
Give me a number.
32.
30. What about flip angle?
5.
Is it T2? Nope.
T2
T2 star.
Gradient echoes can't get T2 weighting.
Nope. So it's T2 star. And then proton density. What would that be?
Oh no. A long TR and a short TE. So like the TR would probably be at like 3,000.
Don't worry about
Gradient
TR,
echo,
Max.
it's
On
always
GRE.
Never mind, never mind. I'm wrong. Sorry.
It's on the screen now. Just read it.
I'm gonna just take my TE down to
Trick me.
no, it is proton density. Right? Low flip angle, eliminating T1 information. Low TE, eliminating T2 information. T2 star information. Proton density now.
What? So it has to have
Disclaimer, contrast parameters will vary. There's a lot of different reasons why these things might look different. It depends on your field strength and it depends on what you're trying to do. But for the purposes of this course and trying to understand these concepts, we will be using these numbers. So memorize these numbers so that we can talk about this stuff. Okay? So let's do something here. Let's do a fun game. When you answer these questions, the first thing you want to do is tell me what type of pulse sequence it is. What type of pulse sequence do we have here?
T1 weighted spin echo.
What type of pulse sequence is it?
But
It
no,
is a
spin echo.
spin echo. Now, what type of weighting do we have? How about this? Start with your TR. Is that a long TR or a short TR?
It's
Long
a proton density.
That's long. Is that a long TE or a short TE?
Okay.
Short. We've minimized T1 information and minimized T2 information. So what do we get?
Proton
Proton
density.
D. Look at that. What do we got?
An echo T2.
Spin echo. Long
It's a-
TR, short TR.
T1.
Long.
No.
Eliminating T1 information. Long TE or short TE? 90.
Long.
Long. Increasing T2 information. And it's a spin echo sequence. It's T2 weighted spin echo. What do I got there?
Gradient echo.
Gradient echo.
Gradient. What's the
Echo
weighting?
T2 star.
T2 star. You're doing it! Right? Flip angle. Small. Minimizing T1 information. Allowing for full longitudinal recovery in that short TR period. Relatively long TE, allowing for some dephasing to happen to generate contrast between T2 star decay. The differences in T2 star decay between different tissues. Help me turn this into a T1 weighted gradient echo.
Increase your flip angle to 75.
Mhm.
Not quite there yet. What else?
Decrease your T. Let's go to 5.
Decrease the
Wait,
TR.
TR doesn't change. Remember, it's always short.
Man.
That's it right there. How do I make it a proton density weighted gradient echo?
Um,
the TE.
That'll work. What else?
Lower flip angle.
Actually, no, that didn't work at all. That would have,
You want low TE and low flipping.
yeah. We were PD before. That's right. We said PD, didn't we? We're trying to get to,
That's T1 weighted.
that's T1 weighted. Let's do, what we're doing, PD?
Yeah, we
Yeah.
want P.
Yeah, how do we do PD?
Lower the flip angle.
Minimizing T1, minimizing T2 star, proton density. There'll be questions like this. There'll be questions about intrinsic contrast parameters, extrinsic contrast parameters, spin echo, gradient
If you
echo.
Sorry, I had a quick question.
What's up?
If you had a question like TR 4000 with the same parameters there, but with no refocusing pulse, would you just say that's like a stupid sequence, basically? Like, would that be the answer?
Yeah, it would be stupid sequence.
Yeah, cool.
Definitely improper parameters. If it was 4,000,
yeah.
I'm not going to get that tricky on these ones. But yes, if it was like this, that's improper parameters. No reason to have a TR like that if this is a gradient echo sequence. But we're going to allow for full longitudinal recovery with a higher flip angle anyway, so there'll be no reason to lower the flip angle at all.
I feel like,
Go ahead.
I was just going to say, the reason I pointed out, because I think Max was getting a little stuck on some of the GRE elements and trying to manipulate TR, but I feel like understanding that before you change it to 90 is a good way to really understand, like, if something is GRE, you want to understand why it's GRE, right? So that it's a shorter time. You want the time, the TR to be short. So you just take that as a given, and then you manipulate the other parameters.
Yep.
Okay.
So yeah, go back to here. The TR is always short on a gradient echo sequence.
Can you just explain to me the proton density for the gradient echo one more time? So it's a short TR, a short TE.
What minimizes TE?
What minimizes TE?
Yeah. How do you get less TEs? How do you less signal from TE?
You decrease it to 15 milliseconds.
Well, you want it small, right? You go
Yeah.
smaller than 15, but so that, and then how do you decrease T1? Or I'm sorry, how do you decrease what am I trying to say?
TE.
How do you minimize T1?
You bring down the TR.
No, forget TR, remember?
Oh man.
What was your original question? Ask that again.
Just for the gradient echo proton density, just like the parameters, like how would you be able to determine it's a proton density.
Okay, so because it's GRE, right, gradient echo, what is the TR going to be? Just because it's a gradient echo sequence.
The TR is always going to be short.
Yeah, cool. And then we want to minimize the other two factors, which are the T1 and T2 star weighting, right?
Yeah, so you
So the
want like
T2.
Minimize your T1 information. How do you do that? By allowing for full longitudinal recovery, right? So how do I do that here? With my flip angle.
you decrease it.
Yeah, no, yeah, you're right. So, short flip angle.
Short flip angle, probably like 25.
What do we put as the parameters on here?
25 or less.
25. 5 to 25. That minimizes T1 information. Now we want to minimize T2 information. How do we do that?
They bring it, it has to be lower than, so like to 15.
It's going to be as small as possible. Let's just say
4 or 5.
Let's just say 5 or below, if we want real numbers, 0 to 5. Take this exact one right here and make it a T1 weighted now.
T1 weighted. So for the T1 weighted, we would have to increase the flip angle between 70 or 90. And then increase, well, the TR has to remain short. The TE is fine where it is.
We're good to go then. You did it.
You just have to change the flip angle.
Yep.
Okay. Yeah, that's my biggest problem. Thanks, guys.
You're welcome. So if you just remember what each one of them control and what you're trying to do, right?
Yeah. Yeah, the
Flip
flip
angle
angle.
controls my T1. TE controls the T2 star, right? If I want more T2 star, I increase my TE. If I want less T2 star, I decrease the TE. If I want more T1 weighting, I increase the flip angle. If I want less, I decrease the flip angle, right? For T1 weighting, I want to decrease T2 weighting. For T2 weighting, I want to decrease T1 weighting, or T2 star, I should say in this case. For proton density, I want to decrease both.
Okay.
The same works for spin echo.
Okay.
It's just done in a different way. Using that TR instead of the flip angle to increase or decrease T1 information.
Okay.
Is it always going to be in increments of like 5 and 10, or could it be like 76, for example, on the flip angle?
It could be, yeah.
Okay.
Yeah, as long as it's within that range that we defined. Take time, do the module. If you've already started it, I would do it again for imaging you. I'll send you this lecture. Yeah, it just takes practice. You know, you gotta think about these abstract concepts in your mind, and it just takes a little bit of time to sort of to make a solid model in your mind of what it means, and then kind of roll it around a little bit till it makes sense. Anyone else have any questions?
I had a clarification. This is a review question, but when I was doing the module, it had like a review section at the beginning, and it labeled the transverse component of the NMV as B1. Is that accurate?
Yeah, it can be B1. It can be described as B1 because it's literally a magnetic field, right? That's transverse to B0. So it can be described as B1. I've also heard the transmit RF as referred to B1 as well.
Yeah, that's what that's what I remember learning. That's why I was wondering.
Yeah.
But they're just kind of used interchangeably, like a lot of the
Yeah, depending on which literature you read, they're both essentially RF magnetization, RF electromagnetic oscillating field that's in the transverse plane. That's in that direction, right? So they can both be the same thing.
When are you going to share this this recording?
Sometime this week. It takes a while for it to finish processing.
Do you have any tips on outside sources besides the book and Imaging You to go over what we just learned today?
I mean, the videos that were in the lecture, I don't have anything else on top of that I know of. The book, yes. This is, it's going to be pretty basic for now. It'll get more complex, right? So if it's, as long as you're generally understanding it, it's going to be okay as long as you keep going over it again and again. Yeah, I think you just have to want to sort of understand it on a deep level, and you'll surprise yourself on how well you do if you're really trying to dig in. So. Once again, there's one discussion forum. It's a substantial one though, so take your time on it. I think it's worth 25 points. Yeah, if you have any questions, please reach out. Otherwise, I will see you all.
Are we still doing Zoom next week as
Yes.
scheduled? Okay. Back to the regular time, 8 a.m., correct?
Yes, please.
Wait, Brian, you said we're also doing Zoom next week again? Sorry, I missed that last.
Yeah, we'll do Zoom next week again.
Thank you.
You're welcome. All right, thank you. Have a great weekend.
Thank you.
Thank you. Thank you. Feel better.
Thanks.
Brian, would I be able to like just talk to you after?
Yeah.
All right, cool.